Right, actually got some questions today preceding the live stream. So one is an organic one question. It was a question about there's an example in the notes where you're given this alkene and it talks about HX addition. And it shows you that you end up getting this product. Oops. The student asked me, like, why does it go to the right? Why wouldn't it go to both? It actually does go to both. So there's not preference here for the left or the right. If there was any preference, it would be for the right, simply because the sterics, these methyl groups are less bulky than the ethyl and the methyl group. But the example there is just kind of given for illustrative purposes. For HX addition, X can be a lot of things. So it can be bisulfate, it can be halide, something like chlorine, bromine, iodine, it can be the hydroxide in water. There are a lot of things, but there's this general pattern, and the notes from there kind of follow into examples of where you get Markovnikov and anti-Markovnikov additions, and what drives those types of additions and why. But in terms of that point in the notes, it's more just kind of meant to say, like, this is just a broad class of reactions. So don't look at H2SO4, or HCl, or HBr, or HI, or H2O as separate reactions. They're all the same reactions. They're just addition across a double bond, and they all obey the same behavior. Now, for organic 2, I got lots of questions. So we'll start working through those. So the homework for organic 2, first question I got was question 15. So it says draw the aldol addition product of this reaction. Now, off the bat, you probably caught, or hopefully caught, that this compound here is chiral, and it's not giving you specified RS. So for a lot of the aldol addition reactions, aldol condensation reactions, you even saw this with the discussion board, we're not going to go through the R and the S, the cis trans. The cis, in terms of cis trans for the aldol condensations, most likely the trans, sometimes we'll get part of the cis, and we're going to generate both the R and the S alcohol. So we're not so much worried about that. What we are worried about is the relative configuration of the final product. So to make this a little bit easier, I'm going to draw, this is an aldol addition with itself. So I'm going to draw the mirror image, and what we're going to do is that we're going to abstract this hydrogen to give us a lone pair. And this is going to attack this oxygen, which will subsequently attack a hydrogen, and it will give us excuse me. This compound here. Now, I'll show you on the desktop with the drawing utility. There is a temptation here to try to make these look really pretty when you draw them. The program does not need them to look pretty. So when it comes to drawing these, draw what works. Tell you what, let me draw. So this is your starting aldehyde. And oops. And I'm going to draw the same aldehyde on the other side, just in mirror image. So if I want to draw the product of the aldol addition, I'm just going to connect this carbon to this carbon, and I'm going to break the double bond, if it will let me. Change that to an OH. And literally, it will accept that. It doesn't care that the structure is drawn in a very ugly way. That's the product. Right? So question 16. So for question 16, we're given pentanal. And we're asked, can this undergo an aldol condensation reaction? So to figure that out, what we need to do is we need to look at the alpha carbon. And if there are two hydrogens on the alpha carbon, then it's capable of going in aldol condensation. The reason being is that if we look at the aldol condensate, so what I'm going to do is I'm going to draw the molecule, same molecule beneath it. When we get the initial attack, we abstract one hydrogen. So there's our first hydrogen to give us this bond. In order to undergo elimination, we need a hydrogen on the next carbon over to the OH that we form. So we need the second hydrogen here to undergoing elimination. So in order to do an aldol condensation, we have to have two. So the aldol addition product has an alpha hydrogen. So what it means when it's asking that question is, if we look at the aldol addition product, is there a hydrogen on this carbon? The answer is yes, and therefore it can undergo aldol condensation. Now, for the condensation product, again, don't worry about drawing it pretty in the program. So what I can do, flip it over to the desktop again. I'm going to draw pentanal, and then beneath it, I'm going to draw it again. So the aldol addition connects this alpha carbon here to the carbonyl carbon. That would break this double bond to give us an alcohol. So if I break that double bond, I get an OH. And now to do the elimination, I'll get rid of the hydrogen on that carbon, the OH group on that carbon, and I'll just draw my double bond in. If I check my work, that's correct. All right, question 17. So we're given 2-methyl-butanal. And we're asked, can this undergo an aldol condensation product? So if we look at the alpha carbon here, there's only one hydrogen. So if we try to do aldol elimination, when we add it to itself, create that bond, create the OH. The question is, can we further eliminate? The answer is no, and there's two ways you can prove this to yourself. One, which is the technical way, there's no hydrogen here to be eliminated. The second is that, let's say we drew the aldol condensate. So we drew this. We have 1, 2, 3, 4, 5 bonds around carbon. We know carbon can't do this in organic molecules, so this would put carbon over valence. So really, we don't have a choice. We have to go with the aldol addition product. So the aldol addition of the 2-methyl-butanal lacks an alpha hydrogen. So when it says alpha hydrogen, it's referring to this carbon. And therefore, it cannot undergo an aldol condensation reaction. And it tells you to draw the structure of the aldol condensate product or the starting material, so you just draw the structure of the 2-methyl-butanal that's above it. All right. Next question. 62. So design a synthesis of ethyl N-ethylamino propionate from ethyl formate, ethyl acetate, and ethyl propionate. And again, this is really obnoxious the way they write this. So you're starting with these compounds. And what you want to make is this compound here. So question 1, choose the best option for the intermediate electrophile precursor to the target molecule. So we're starting with this compound here, and we want to know how to go backwards. All right. Give me a minute to think about this. Amine chemistry I'm not so good at. So the nucleophile is the one that does the attacking, the electrophile is the one that gets attacked. So if I had to gander, I'll show you what the options are on the desktop. So we've got A, which already has a nitrogen double bond, B, which already has a nitrogen atom, C, which is an aldehyde, D, which is a double ester, and E, which is pretty much the compound we're starting with minus that substitution. So if I had to gander, this amine can be formed by the reaction of ethylamine with an aldehyde. So if I start with an aldehyde, this would react with this through basically what looks like an aldol addition, but because the nitrogen has an additional hydrogen on it, it would end up forming a double bond with the, basically we end up clipping this off and forming a double bond with the nitrogen. Now, this is more stable than the amine, so their ester here is a lot more stable than this. So if I had to guess, I would say the starting one here is actually C, the aldehyde, but we'll see if I'm right. So we pick the aldehyde. Tells me I'm correct. All right. So, and again, it tells you the ester aldehyde can accept the appropriate nucleophile at the aldehyde carbonyl carbon to provide the target molecule in one step. So again, the idea here is that the nitrogen is more selective to attacking the aldehyde than the ester. And so if we edit ethylamine, that N2 with an ethyl group hanging off of it, we would get the desired product. Now I'll choose the best nucleophile. I've just said it, it's B, it's this amine group. All right, so what's the best precursor to, back it up. What's the best precursor to this compound here based on our starting molecules? So let's take a look at the options here. It's so confusing to go backwards. What? The precursor to the ethylamine. Best precursor. What would you need to make ethylamine? So if I had to choose one for the ethylamine, I'll show you what my confusion is. So they're asking you how you would make this compound here, the CH3, CH2, N2. I would honestly say the CH3CN because you can just hydrogenate that. Oop. There is more fish way from the design starting materials. Okay. So from the design starting materials, I would say that probably C. Wait, did it say I was correct? Oh, sorry. So if it's not that, then my guess would be this one because you can easily decompose this one with water to give you formaldehyde and the... Really? More efficient material starting material. So we know it's not the alcohol. What on earth? Starting materials. starting to run out of options here. I wouldn't pick C. I mean, E, in principle, you could do a substitution reaction, but I'm not seeing why. I mean, if I just had to guess, I'd say D. Apparently it's D. Convert it in one step. I'm guessing this is hydrogenation, but again, I don't know why you wouldn't go with B, where I could just run that over hydrogen catalyst. Okay, whatever. Choose the best precursor for the acid halide, and so many good choices. So D is the most reactive. So that's going to be my guess here, is that if we start with D, the acyl chloride is pretty easy to react. But it keeps doing this weird thing where it says based on the starting precursors. So let's see here. Let me guess. I really don't think y'all know what efficient really means. From the designated starting materials. Well, one of these is a starting material, so I'm going to go with A. Oh, that's okay. Choose the best option for the precursor to the acid analyte intermediate. So this, at least we can start with something we have. So this is the electrophile. This is the one that's most positive. Let me write up the precursors on the board behind me really quick. Like, I'm really confused what they mean by the starting precursors. These are bad starting precursors, but whatever, it's a problem. So if I had to pick starting precursors based off what they have, I would say this compound and this compound would be good starting precursors, because I could just hit that with, well, even then hitting that with a little bit of base would be tricky. But in principle, this could attack the carbonyl and give us the structure we want. So the electrophile in this case is going to be the aldehyde. Yep. And then the electrophile is going to be, where are you? Right there, compound E. So these are both starting precursors. All right. So here's the overview. This is a really complicated synthesis. Good problem, but really complicated synthesis. We're going to start with ethylamine. This is going to react with these, and apparently we're reacting our starting compounds to make these. So now we go to the next part, which are the reagents necessary. Probably the reagents. So choose the appropriate reagents. So we're going to convert the ethyl acetate to acid amide. This we're going to want to be careful with. I'm going to go with ammonia. Yep. So ammonia will attack the carbonyl, give you that compound. Choose the reagent to convert it to this. Oh my goodness. All right, we're going to need a fairly aggressive reducing agent. So that would convert it to the alcohol. I'm curious. I wonder if you can just reduce it off. Nope. Yeah, that would just give you the alcohol. Satisfying my curiosity. So H2SO4 is not a reducing agent. Sodium borohydride might work, but my guess is they're looking for lithium aluminum hydride. Yep, so lithium aluminum hydride will be strong enough to reduce off that oxygen to give you the ethylamine. Now it's looking for the reagents to convert this to this. If I had to pick one, I would definitely say the tert butoxide. We need to deprotonate this to give us the ion, so we get a TAC, but I wouldn't want to work with anything small like sodium hydroxide. Most likely it will decompose these esters. In fact, this is kind of what 252 is doing in the lab this week, is they're using a base to decompose an ester. This eth oxide would be a nice second choice, because if it does attack the carbonyl, it's not likely to give us like anything other than our current product. So that's going to be my first guess, is tert butoxide. Nope. Oh my goodness, you're so far up the page. So this is going to be my second guess. Yep. So yeah, I would recommend tert butoxide just because I think it's too bulky to interact. They're claiming the eth oxide works better because if it does attack, you're not going to notice. You're still going to get the same product. And that's it. Man, that's a long synthesis. Good problem, but it's a long synthesis. Right, 74. By the way, you won't see anything that ridiculously hard on the exam. Identify the principal organic products of the following reaction. And they're definitely giving you stereochemistry for a reason. We've got hydroxide. This is going to go underneath nucleophilic attack. It's going to get us an inversion. So instead of these being up, we expect these to be down and the OH to be up. So I'm guessing the difficulty with this problem is just drawing the final product more than anything else. So let's bring it to the desktop. Now it's going down here. It's actually going to go up. So in this case, I've inverted the symmetry. So I've got the CH3 groups pointed down. I've got the OH group pointed up. Let's see if it accepts that answer. Hoffman elimination. A proton is removed from the quaternary amine to produce the less substitute alkene. But there's no hydrogens on the amine. What's the solution? Okay, sorry, Hoffman elimination. Didn't think about that off the top of my head. So for the Hoffman elimination, basically you're going to get the hydrogen abstracted off the carbon, and you're going to end up with the alkene instead. Sorry, didn't recognize that one. So yeah, what it's saying is actually you don't get this substitution. What you get is you actually get a hydrogen eliminated off this methyl group. So you've got a CH3 with 3 hydrogens. One of these hydrogens is popped off. Man, let's draw that a little bit better. So you can extract a hydrogen. That's going to create a double bond that's going to break this. And so we're going to end up getting this compound here. So we're just going to form an alkene instead. Sorry, I just recognize the Hoffman Elimination looking at it. 74, 77. Yeah, amines are not my strong point. What is the product of the following reaction sequence? Another amine. Let's see here. Well, the water would apply an alcohol now, wouldn't it? Give me a minute. Okay. Coming back to me now. So I'm going to try to work this one. So got this lone pair. Lone pair can kick down, create a lone pair here, and we're going to get formal charges. This negative can displace the chlorine, and this is going to give us this intermediate. So now our Cl minus can attack the nitrogen. They're going to be paired together. Now we're going to break that bond, kick it back to give us a lone pair. Again, amines are not my strong suit. And any water present, I'm guessing the hydroxide here is going to attack. So this is the first step. This is what your amine is going to do, is form this bond here. Now we add an OH group to it. So we have OH, we have H2O. Hold on, let me think about this. Because I know this step's right. It's how you go from here. your next resonance is this. And if that extracts a hydrogen, get the ketone. Oof, okay. So, a lot of mechanistic errors here. So, first step. Nitrogen is going to form a double bond, kick up this lone pair, and we're going to get a short-lived resonance structure. It looks like this. This anion carbon here is going to attack our chlorobenzene. Make sure you can still see that on the video. So we've got chlorobenzene. That's going to attack, knock the chlorine off, and it's ultimately going to give us this product. Sorry, not 6,5. All right, next step is we're going to put the lone pair back. And we're going to get this compound here. I'm just going to draw a little ring here because I'm trying to draw long 5-member rings. So this is going to give us a carbocation. The carbocation here is going to react with water. So we have water, it's under acidic conditions, but we still have OH minus. The hydroxide that's just floating around in the water, actually we can probably even do it with just water. This is going to get attacked by the water and it's going to give us, we're running out of space here. Hopefully you can still see it. Guess I can bring up the camera. So a few things are going to happen here. First, the nitrogen is going to take a hydrogen. This is basically just going to move the charge around. We're going to have the oxygen take another lone pair and form a double bond with the ring. This will break the nitrogen-carbon bond, and then the lone pairs that are formed by that are going to extract the hydrogen. So the end result of all of this is this compound. So we've got a benzene ring, bridging carbon, our cyclohexane with a ketone. There's a lot that's going on here. Basically, you're hydrolyzing a carbon-nitrogen bond, and that's how you end up with the ketone. So, yeah, it's a lot of steps, but the correct answer when you finish is this one down here, the ketone. All right, see a question up in the discussion board. Hi, Professor Gare, with the third structure on the saponification line worksheet. I'm sure how to get the product too. So let me, I wonder if I have quick access to that lab manual. Let's see. All right, this one I can actually answer. So for the saponification of this molecule, 5. We're going to have the hydroxide attack that carbonyl and break carbon-oxygen bond there. So our first step, first intermediate here, is going to be the carboxylic acid. And the alkoxide. This alkoxide is going to extract the hydrogen off the carboxylic acid. And so when you finish, you're going to get the carboxylate ion and the alcohol. And with all these, you're going to finish up with the carboxylate. You're not going to finish off with the ethoxides or the alkoxides. Basically, the alcohols minus the hydrogen, because they're way too basic. As the name implies, carboxylic acids are acidic. How do you name that? So this is going to be your parent. Cyclopentane carboxylic acid. And then if I had to guess, 2-hydroxy ethyl cyclopentane carboxylic acid. So let's see if I'm right. That's what Google's for. Oh, you need to name the position too. So 2-hydroxy ethyl cyclopentane carboxylic acid. And the way you can cheat to check your name is just search Google search, and PubChem will probably tell you if you're right. Yeah, you're welcome. Can you go over question 89 for the test for homework? Not confident on the chiral center of the epoxide. I think I know which one you're talking about, actually. But let's bring it up. Ah, this one. So we've got one butene. Peroxyacetic acid is going to give us a carboxylic, or epoxide. The question is whether or not there's one or two stereoisomers. So there's actually two stereoisomers, because if you look at this carbon here, so this one has two hydrogens, so it's achiral, 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 but this one has an oxygen, a carbon connected. This one has an oxygen connected to a carbon, this one has a carbon connected to an oxygen, and it has CH2 and a hydrogen. So there's actually the two stereoisomers. You've got one where it's wedged, and then you'll have one where it's dashed. Now the R and the S is where it's going to get challenging. So really we just got to identify one, and the other one's going to be the reverse. And actually it's going to be a lot easier if we draw the hydroxide and the epoxide in its own plane, and we weigh whether this group coming off here is out or in. So looking at this one, lowest priority is hydrogen. Highest priority is going to be oxygen. We've got a carbon and carbon. This carbon is connected to an oxygen and two hydrogens. This carbon is connected to a carbon and two hydrogens. So this is going to be the second highest priority. This is going to be the third highest priority. So looking at that, hydrogen's going back 1, 2, 3. This is the S configuration. So this should be the R configuration. So let's see if I'm right. Nice thing is, if I'm wrong, all I have to do is just flip it from wedge to dash. It's called gaming the system. Yep, R and the S. So on the discussion board for organic 2, do we go from the aniline to the diazonium to phenol, then add the carboxylic acid since the OH group is orthopara? Yes, that's correct. That's part of it, is to get you to kind of go all the way back to test 1 where you had directing groups. So you can convert the amine. You can either make the carboxylic acid and then convert the amine to an OH group to give you the phenol, or you can make it a phenol first and then add the carboxylic acid. If we wanted them to be meta, so in the second position, then we would add the carboxylic acid first and react away the amine to give you the phenol. But in this case, since we want an orthopara, you're going to react away the amine first, because the OH group is an orthopara director. See, it's all coming full circle. Yeah, you're welcome. So for question 88, is a BR seal attached to the alkene or is it just the BR? Also, I'm surprised that we only have one attempt for part 2. So question 88. Actually, let me open that back up. There may be a reason why they're locking you out. Let me take a look at it, but there's probably a reason they're locking you out with just one submission on part 2. There's probably like a 50-50 chance of getting it right. All right, question 88. So paranoid with the desktop up. The organic synthesis of Z2-pentene and bromine and carbon tetrachloride. 2 stereomeres are formed. Draw both. So the carbon tetrachloride, CCl4, this is just a solvent. So there's going to be no chlorine involved with this reaction. It's just there to solubilize these two. You're going to get the bromines adding, but they're going to be added on opposite sides. So your final product will be that or that. But these are definitely two stereoisomers. So I would say definitely you get two stereoisomers. Oh dear, the 2R, 3R, and 2S, 3S. Well, the upside is we just have to figure out which one's the R because apparently the other one's going to be R as well. So I'm going to start with this one because it's the easiest. So bromine up here is the highest. This is a carbon bound to a carbon, 2 hydrogens. It's going to be third, second. So look at it. This is the R. So hopefully this is the other R, which make this S and S. So let's see if I'm right. And it says I got 3 attempts on part 2. Let me check. Okay, that would be, appears to be correct. Cool. Yeah, and it's going to rearrange it to do its own little thing, but I prefer to work in a way that's just a lot easier to draw it out and see it. It's that one. So yeah, the way I worked it was I just took the double bond and just added them on opposite sides. The key actually rotates that back in, which is why they both appear to be on the same side on both of them, both wedges, both dashes. It doesn't matter. Again, 0.004 points for a full question, 0.002 points if you miss that part. Yeah, you're welcome. Floorboards are creaking. So again, if you ever have questions, feel free to email them in advance. I'm just going to come off a couple minutes early because I need to take care of some emails. But again, always feel free to email your questions in advance. Thanks for showing up, and I'll see some of y'all tomorrow.